Section 1.4 Prime Factorization. In this video we will learn the definition of a factor and what it means to be divisible, how to apply divisibility tests, what makes a whole number prime, the definition of a composite number, how to find prime factors with a factoring tree, what is an exponent. Section 1.4 Prime Factorization. In the statement 3 times 4 equals 12, the number 12 is called the product, while 3 and 4 are called factors. Example 1. Find all whole number factors of 18. Solution. We need to find all whole number pairs whose product equals 18. The following pairs come to mind. 1 times 18 equals 18, 2 times 9 equals 18, and 3 times 6 equals 18. Hence, the factors of 18 are, in order, 1, 2, 3, 6, 9, and 18. Divisibility. In example 1, we saw 3 times 6 equals 18, making 3 and 6 factors of 18. Because division is the inverse of multiplication, that is, division by a number undoes the multiplication of that number, this immediately provides 18 divided by 6 equals 3, and 18 divided by 3 equals 6. That is, 18 is divisible by 3, and 18 is divisible by 6. When we say that 18 is divisible by 3, we mean that when 18 is divided by 3, there is a 0 remainder. Divisible. Let a and b be whole numbers. Then a is divisible by b if and only if the remainder is 0. When a is divided by b, in this case, we say that b is a divisor of a. Example 2. Find all whole number divisors of 18. Solution. In example 1, we saw that 3 times 6 equals 18. Therefore, 18 is divisible by both 3 and 6. 18 divided by 3 equals 6, and 18 divided by 6 equals 3. Hence, when 18 is divided by 3 or 6, the remainder is 0. Therefore, 3 and 6 are divisors of 18. Noting the other products in example 1, the complete list of divisors of 18 is 1, 2, 3, 6, 9, and 18. Example 1 and example 2 show that when working with whole numbers, the words factor and divisor are interchangeable. Factors and divisors. If C equals A times B, then A and B are called factors of C. Both A and B are also called divisors of C. Divisibility tests. There are a number of very useful divisibility tests. Divisible by 2. If a whole number ends in 0, 2, 4, 6, or 8, then the number is called an even number and is divisible by 2. Examples of even numbers are 238 and 1,246. 238 divided by 2 equals 119, and 1,246 divided by 2 equals 623. A number that is not even is called an odd number. Examples of odd numbers are 113 and 2,339. Divisible by 3. If the sum of the digits of a whole number is divisible by 3, then the number itself is divisible by 3. An example is 141. The sum of the digits 1 plus 4 plus 1 equals 6, which is divisible by 3. Therefore, 141 is also divisible by 3. 141 divided by 3 equals 47. Divisible by 4. If the number represented by the last two digits of a whole number is divisible by 4, the number itself is divisible by 4. An example is 11,524. The last two digits represent 24, which is divisible by 4. 24 divided by 4 equals 6. Therefore, 11,524 is divisible by 4. And 11,524 divided by 4 equals 2,881. Divisible by 5. If a whole number ends in a 0 or a 5, then the number is divisible by 5. Examples are 715 and 120. 715 divided by 5 equals 143, and 120 divided by 5 equals 24. Divisible by 6. If a whole number is divisible by 2 and by 3, then it is divisible by 6. An example is 738. First, 738 is even and divisible by 2. Second, 7 plus 3 plus 8 equals 18, which is divisible by 3. Hence, 738 is divisible by 3 because 738 is divisible by both 2 and 3. It is divisible by 6. 738 divided by 6 equals 123. Divisible by 8. If the number represented by the last three digits of a whole number is divisible by 8, then the number itself is divisible by 8. An example is 73,024. The last three digits represent the number 24, which is divisible by 8. 24 divided by 8 equals 3. Thus, 73,024 is also divisible by 8. And 73,024 divided by 8 equals 9,128. Divisible by 9. If the sum of the digits of a whole number is divisible by 9, then the number itself is divisible by 9. An example is 117. The sum of the digits is 1 plus 1 plus 7 equals 9, which is divisible by 9. Hence, 117 is divisible by 9, and 117 divided by 9 equals 13. Prime numbers. We begin with the definition of a prime number. Prime number definition. A whole number other than 1 is a prime number if its only factors, or divisors, are 1 in itself. Equivalently, a number is prime if and only if it has exactly two factors or divisors, 1 in itself. Example 3. Which of the whole numbers 12, 13, 21, and 37 are prime numbers? Solution. The factors or divisors of 12 are 1, 2, 3, 4, 6, and 12. Hence, 12 is not a prime number. It has more than two factors. The factors divisors of 13 are 1 and 3. Because its only divisors are 1 in itself, 13 is a prime number. The factors or divisors of 21 are 1, 3, 7, and 21. Hence, 21 is not a prime number. The factors or divisors of 37 are 1 and 37. Because its only divisors are 1 in itself, 37 is a prime number. Example 4. List all the prime numbers less than 20. Solution. The prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. All of these numbers have only divisors 1 in themselves. Composite numbers. If a whole number is not a prime number, then it is called a composite number. Example 5. Is the whole number 1,179 prime or composite? Note that 1 plus 1 plus 7 plus 9 equals 18, which is divisible by both 3 and 9. Hence, 3 and 9 are both divisors of 1,179. Therefore, 1,179 is a composite number. Factor trees. We will now learn how to express a composite number as a unique product of prime numbers. The most popular device for accomplishing this goal is the factor tree. Example 6. Express 24 as a product of prime factors. Solution. We use a factor tree to break 24 down into a product of primes. At each level of the tree, break the current number into a product of two factors. The process is complete when all of the circled leaves at the bottom of the tree are prime numbers. Arranging the factors in the circled leaves in order, 24 equals 2 times 2 times 2 times 3. The final answer does not depend on product choices made at each level of the tree. Here is another approach. The final answer is found by including all of the factors from the circled leaves at the end of each branch of the tree, which yields the same result. 24 equals 2 times 2 times 2 times 3. Alternate approach. Some favor repeatedly dividing by 2 until the result is no longer divisible by 2. Then try repeatedly dividing by the next prime until the result is no longer divisible by that prime. The process terminates when the last resulting quotient is equal to the number 1. The first column reveals the prime factorization, i.e. 24 equals 2 times 2 times 2 times 3. The fact that the alternate approach in example 6 yielded the same result is significant. Unique factorization theorem. Every whole number can be uniquely factored as a product of primes. This result guarantees that if the prime factors are ordered from smallest to largest, everyone will get the same result when breaking a number into a product of prime factors. Exponents. We begin with the definition of an exponential expression. Exponents. The expression a to the m is defined to mean a, and so on m times. The number a is called the base of the exponential expression, and the number m is called the exponent. The exponent m tells us to repeat the base a as a factor m times. Example 7. Evaluate 2 to the 5th, 3 to the 3rd, and 5 to the 2nd. Solution. In the case of 2 to the 5th, we have 2 to the 5th equals 2 times 2 times 2 times 2 times 2 5 times, which equals 32. In the case of 3 to the 3rd, or 3 cubed, we have 3 to the 3rd equals 3 times 3 times 3, 3 times, which equals 27. In the case of 5 to the 2nd, or 5 squared, we have 2 factors of 5, which is 25. Example 8. Express the solution to Example 6 in compact form using exponents. In Example 6, we determine the prime factorization of 24 equaling 2 times 2 times 2 times 3. Because 2 times 2 times 2 equals 2 to the 3rd power, we can write this more compactly as 24 equals 2 to the 3rd power times 3. Example 9. Evaluate the expression 2 to the 3rd power times 3 to the 2nd power times 5 to the 2nd power. Solution. First, raise each factor to the given exponent, then perform the multiplication in order from left to right. So 2 to the 3rd equals 8, 3 to the 2nd is 9, and 5 to the 2nd is 25. Then 8 times 9 is 72, and 72 times 25 equals 1800. Application. A square is a rectangle with 4 equal sides. Area of a square. Let S represent the length of each side of a square. Because a square is also a rectangle, we can find the area of the square by multiplying its length and width. However, in this case, the length and width both equal S. So A, or area, equals S times S equals S squared. Hence, the formula for the area of a square is A equals S squared, or S to the 2nd power. Example 10. The edge of a square is 13 centimeters. Find the area of the square. Solution. Substitute S equals 13 centimeters into the area formula. So the area would be 13 times 13. Hence the area of the square is 169 centimeters squared, i.e.